Good morning, dear students. Today we are going to discuss classroom discussion topic CDT1, that is crystallography. After completion of this class, you will be able to differentiate between atomic or molecular structure of crystalline and non-crystalline materials. So to understand the crystallography, you should be able to know the difference between crystalline and non-crystalline materials. Next, draw unit cells for face-centered cubic, body-centered cubic, and hexagonal close-packed crystal structures. In fact, there are many crystal structures, but we focus mainly on face-centered cubic, body-centered, and hexagonal close-packed crystal structures because these are found in majority of the materials. Now we will see what is crystallography. The engineering materials are aggregate of atoms which bind to one another in a regular pattern. Their properties mainly depend upon the nature of the atom and on the manner in which atoms are assembled. You studied this crystallography in or in chemistry, but again we are revising here. Okay, so the properties, mechanical properties or thermal properties, physical properties, chemical properties, all will depend on nature of atoms and the manner in which they are arranged or assembled. Crystallography is the study of the arrangement and dispersion of atoms within the solid. Solids are generally classified into crystalline solids and non-crystalline solids. Now, what are crystalline solids? Now, you can see the figure here. In this, the atoms are arranged in a definite pattern. Okay, constantly repeated in three dimensions. Therefore, the crystalline solids have a definite geometrical configuration, characteristics of the substance. So you can see in three dimensions, the pattern is repeated. Each atom is fixed at a definite regular orientation and is at a definite distance. The distance between two atoms is fixed to all other atoms surrounding it. Okay, so these arrangements are responsible for various properties like rigidity, the volume, diffusion, and melting point. So one point we should keep in mind that in crystalline solids the pattern is definite, not indefinite, whereas so examples of crystalline solids are for example aluminium, copper, and iron. So these are the commonly used materials in you know uh, domestic applications, industrial applications. Now coming to non-crystalline or amorphous solids, you can see the difference between crystalline and non-crystalline materials. The figure here shows that the pattern is not definite, it is not regular. So these have no definite geometrical form and no regularity in the arrangement of atoms in a solid state. The internal structure is not based on a regular repetition of the pattern. Although they are rigid and incompressible, they do not have sharp melting points. Whereas in crystalline materials, the melting point is sharp, that is fixed to melting point, like 550 degrees centigrade. For copper, it is around 750 degrees centigrade. Whereas in crystalline or amorphous solids, non-crystalline materials also called as amorphous solids. So they do not have definite a melting point. Okay, that melting point ranges. So as a range, the melting point is ranging over certain temperature. Okay, so examples of these non-crystalline solids are glass, ceramic, rubber, bakelite, and cellulose. Now coming to next, the most important terms we are going to study related to the crystallography, space lattice or crystal lattice. Now to understand crystallography, crystal systems, crystal structures, okay, we should understand these basic terms like space lattice or crystal lattice. Now, what is space lattice? Atoms of a crystal are arranged in a repeating three-dimensional patterns. An array of atoms is arranged in a definite angular arrangement of the space positions called space lattice or crystal lattice. These repeating patterns in crystals are due to atomic coordination within the material, which contribute to the physical shape of the crystal. Now, space lattice you can see here, these two diagrams, clearly indicate what is space lattice. So you can see all the, now this is the like a cube here, okay. So right side diagram is showing like a cube and all the points are there, okay. So these points, if replaced by atoms, then it will become, space lattice for space lattice of atoms. Okay. So if I consider now here, you can see here, this is the unit cell here. So cubical unit cell, right? And these points, now cubical unit cell means what? It will have 8 corners. Okay, 1, 2, 3, 4, 5, 6, 7, 8. One is hiding behind the cube. So 8 corners are there. 8 points are there actually. And if I replace these points by atom, then it will become a space lattice or crystal lattice. Okay, and these points here you can see this is lattice position and in three directions x, y, xy and z direction. The same is with the crystal lattice. You can see all the atoms are indicated here as the spheres. Okay, so actually this is called as the sphere model. Now if I join all the centers of the atoms, if I join all the centers of the atoms here, you can see it will become a cubical unit cell. Okay, the shape of the unit cell is cube here. So if I repeat this pattern, okay, so you can see this pattern is getting repeated in three directions. So this is called as the space lattice or crystal lattice. So space, this is a three-dimensional structure and this is the skeleton. The right side figure is the skeleton structure and this is the three-dimensional structure. Now, what is unit cell? So here we defined what is this. We talked about this unit cell. Okay. Now, what exactly is the unit cell? So unit cell, you can see here one cube is taken from the space lattice here, and we indicated in this slide. Okay, so you can see there are 8 corner atoms here, and three crystallographic axes are there: x, y, and z. Okay, and you can see here these are the three angles. You can see these are the three angles alpha, beta, gamma, and the distance between two atoms is indicated as a. Since it is a cube, all the sides of the cube are same. So what is unit cell? So the smallest portion of a crystal lattice that can be used to describe the lattice is called the unit cell. It represents the space lattice as a whole since it is identical with every other cell in the lattice. So this cube will be same as that of the other in the lattice. It can be constructed by joining unit cell repeatedly in three dimensions as discussed earlier. The lattices of various metals differ in the size and shape of their unit cell. So this the size, that is the sides of this cube, are different for different materials, and these angles alpha, beta, gamma, these are the angles uh, called as the crystallographic angles. They are different for different materials. Now, what are the lattice parameters or lattice constants? The size and shape of unit cell can be described by the three vectors magnitude A, B, C drawn from one corner of the cell called crystallographic axis. The angles between them, alpha, beta, gamma, which subtended with the axis, are called interfacial angles or crystallographic angles. These lengths and angles are called as the lattice parameters. So they are also called as the lattice constant of the unit cell. Now the dimensions of the lattice given by lattice constants is in angstroms. All of you know 1 angstrom is equal to 10 power minus 10 meter. Represent the distance between the parallel planes of atoms comprising the unit cell and the angles alpha, beta, gamma expressed in degrees or radians. The lattice parameters may be or may not be equal. This gives rise to formation of different crystal systems. Now, what are the crystal systems? Okay, so the atoms coordinate with neighbors to form a solid with specific patterns. These patterns are in 7 crystal systems. Okay, A.J. Bravis, a French mathematician, showed that there could be only 14 possible basic unit cells associated with the 7 crystal systems. Okay, so with the help of 7 crystal systems, you can form 14 basic structures. So what are these crystal systems? So uh, these 14 lattices are popularly known as Bravis lattices. Bravis lattices of 7 crystal system. Now you can see here this figure indicates or this table indicates lattice constants of each unit cell geometry. For example, here crystal system is a cubic axial relationship ABC. In earlier case, in a cubic system, I took this as A, but in some cases it may not be same. Since it is a cube, all the sides are same. If it is not cube, then sides may not be same. So that's why it is indicated as ABC in crystal system. Okay, to describe various crystal systems. So axial relationship, the lengths A is equal to B is equal to C, and angles are alpha, beta, gamma equal to 90 degrees. So unit cell geometry, you can see A, B, C are same in this, and all angles are same. That is 90 degrees here. You can see this is a 90 degrees. Coming to next system, hexagonal. So here A is equal to B. So now you can see hexagonal at the bottom. The shape of this system is a base. The base is hexagon, bottom base and top base. So here A is equal to B, but the height is different. Is not equal to C here. So it is not equal to C. So alpha is equal to beta 90 degrees, but gamma is 120 degrees. All of us know that in hexagon the angle is 120 degrees. Next system is tetragonal, wherein A is equal to B is not equal to C. Here A is equal to B, you can see here, but height is C different, and alpha is equal to beta is equal to gamma equal to 90 degrees. So this is a 90 degrees. Okay, angles are 90 degrees. Next system is rhombohedral. Here you can see it is similar to tetragonal, but angles are not equal to 90 degrees. A is equal to B is equal to C. It's a cube. It's like a cube. Cube tilted. Okay. A is equal to B is equal to C, but angles are not 90. Somewhat, it's like a rhombus. Next system is orthorhombic. Here you can see A is not equal to B is not equal to C, whereas angles are 90 degrees. So all sides are different in orthorhombic. Whereas in next is the monoclinic, where all sides are not equal. All sides are not equal. Whereas alpha is equal to gamma. So here you can see alpha is equal to gamma is 90 degrees, but it is not equal to beta. Okay, these are the some lattice constant for different systems. We have to remember them. Next, triclinic, A is not equal to B is not equal to C. You can see here at the bottom A, B, C are different, as well as all angles are not 90 degrees, as well as they are not equal. Angles are not equal. The angles are angles are different. Now you can see all these structures. You can see simple monoclinic, end-centered monoclinic, triclinic, hexagonal, rhombohedral, simple orthorhombic, body-centered orthorhombic, end-centered orthorhombic. All these systems and structures are available in textbooks like VD Kodgiri and these are well described in Callister book. I strongly urge the students to refer Callister book. So the previous 14 lattice structures are here. Okay. Now this is a face centered orthorhombic, simple cubic, body centered cubic, face centered cubic. Okay. So here simple cubic atoms at 8 corners, body centered cubic. In addition, one more atom is there at the center. You can see here one more atom at the center. In face centered cubic, there is no atom at the center, but one additional atom is there on each face. So there are total 6 faces for a cube. 1, 2, 3, 4, 5, 6, front and back. Okay, so 6 additional atoms will be there. So total 1, 2, 3, 4, 5, 8 plus 6, 14 atoms will be there in a unit cell. Here only 8 atoms, here 9 atoms, here 8 plus 6, 14 atoms. Okay, and here simple tetragonal, you can see body center tetragonal, same as that of the cubic, but it's a tetragon. Now reflection spots. Having discussed the concept of crystallography, here are reflection points. Question number 1. Which type of solids have variable melting points? Which type of solids have variable melting points? We will give 10 seconds of time. We studied types of solids, crystalline solids and non-crystalline solids. We discussed the melting point of both the solids. Now, which solid has variable melting point? Answer should be non-crystalline solids. So they have a range of melting point. Okay, points. Now, next question. Question number 2, which was asked in GATE exam. What are the atomic packing factors of BCC, FCC, and HCF crystal structures? Actually, this question is related to next class. Question number 3. How many Breve system and crystal structures are there? As we have seen earlier, just now, okay, there are what should be the answer? What should be the answer? I am expecting the answer from the students. So there are 7 Breve system and 14 crystal structures.